In this video, we are going to go ahead and hook up our users model to our authentication system. But we have a problem because we're going to be using our users model for validating passwords, and in our users model we have something called a password hash. We haven't really talked about what a hash is or why you would want to use one. A very naive implementation of usernames and passwords would be something like you would have a users table and it would have an ID, a name, and a password, right?
Correct.
And the ID might be 1, name might be Nelson, and password might be test. To Steve things. So this is a very naive implementation. The reason why it's naive is if we store these passwords in plain text in the database so that we can validate against them later, we run the ridiculous risk of, if a person ever gains access to our database, they know the passwords of all our users. That's not only problematic for the security implications, it's also problematic actually at a sociological level, because most people use the same passwords for all their services.
Yep. So now they can access everything.
Right. It is a ridiculously irresponsible oversight as part of, or of the part of the web developer, to ever let a plain text password even touch a database in any way, shape, or form. And I'm emphasizing this as much as I possibly can. If you are storing clear text passwords in your database, watch this video and stop doing that now.
Yeah, you could lose your job, and a lot of people could get hurt bad.
Yes. And it has happened quite a few times. So what's the solution? Well, there's two factors to it. When people started to discover that storing passwords in clear text was a really, really, really bad idea, like 20 years ago, people started figuring out ways to prevent doing that, but still allow us to match a password to a password that was typed in by the user. How do you do that? How do you make it so the password is available in the database, but still can be matched against a password by the user? Now, some people would say, oh, well, I'll just encrypt this.
I'm sad because I was going to say encrypt, and now I know that's going to be wrong.
It is wrong. The process of encrypting implies that it is possible to decrypt the passwords. Basically, this means that if you encrypt the password, you have to have the decryption key somewhere on your website so your website can decrypt them. Which means that if a person gains access to your database, they're most likely also going to probably maybe have access to your encryption key, and then there's the problem again.
Gotcha.
We don't encrypt passwords.
All right.
We hash passwords. What is a hash? A hash is a function that takes in text and prints out text. But it has a few characteristics. I'm going to invent a hashing algorithm for the purposes of this video. It's not actually going to be implemented or anything. I just want to simplify things. There are many hash algorithms available, and I'll talk about why we're using one over the other once we talk about the basic fundamental quality of every hash function. So on the left-hand side is input, on the right-hand side is output. One of the qualities of a hash function is that it is impossible to go from one value to another. For example, let's say in my imaginary hash function, A turns into 157B12.
Okay.
The idea is that whatever you put into the hash function and you get a hash out of, you can't go back. There's no way to go from 157B12 back to A. I mean, not directly, and we'll talk about that later. Next, even closely related hashes are vastly different. What I mean by that is, let's say we put in A1 or 1A and we hash it. We should get back a good hash function will return something FC10, something like that. It'll return a completely different value.
All right.
So similarities in the input do not equal similarities in the output. The other characteristic of hashes is the same input will always produce the same output. So, the characteristics of a hash function are: the input is vastly different from the output. Second, slightly different input results in vastly different output. Third, the same input will always equal the same output. So how do we use this to store passwords? Well, when we register, we hash the password. So when we register, the user enters a password in plain text. Plain text.
In this case, say test per Nelson. Yeah.
So they insert a plain text password. Let's call it just test. That's the password. It gets hashed and stored on the database as a hashed value, and let's just say 715B20. Okay?
Okay.
So that's registering. So how do we log in? Well, the process is actually fairly straightforward. The user enters a username and a password. The username is used to retrieve a user from the database. So the username, let's say that they properly put in the correct username, and they will retrieve this. They're never going to retrieve the plain text password that they originally typed into the register form. They're going to retrieve the hash that's stored in the database. Then their plain text password is going to be hashed by the same function. If this equals this, so if this hash, so let's say this is 715B20, so they inserted the correct password. If these two values are the same, that means they typed in the same characters that they typed in when they registered their account.
Alrighty, it's making sense so far.
So does this the login register make sense so far as how it protects your password?
Yeah, the only thing I don't understand is if it always returns the same value, then why isn't it breakable just like an encryption?
That's a good question. That leads us into the differences between certain hash functions.
Okay.
So as long as you're good with the process of why we hash, there's actually one more thing that I want to talk about, and those are salts. A salt is where you actually store two values. You store your hash, and you store a random salt. And let's say the salt is another random number, so 158. So this is the hash, and this is the salt.
Yep.
And what happens is the salt is generated when we register. The salt is actually added to the hash when we hash it. So we say hash plus salt, and then hash plus salt. This increases, this actually fights against the ability for people to type in weak passwords such as test, because test is probably a very well-known, it's a dictionary word, and there are reverse lookup tables between most hashed functions that include the word test.
Okay.
A salt prevents the ability, or at least makes it very difficult for people to crack relatively easy dictionary passwords.
All right.
So that slightly addresses what you were talking about.
Okay.
So the practice of using a salt is very important. So let's talk about what?
So when you create your password and you also get your salt of 158, when you type in when you go to log in, is just like the hash, is the salt always going to be that same number?
Yes, it's going to, well, for this user.
Yeah.
And the salt isn't regenerated when we log in. The salt is retrieved from the password and then added on to the plain text password, then hashed, then it gets the value.
Gotcha.
But, so those are just the terminology, the bits of terminology and the processes about password hashing. But there are problems with password hashing. Most hashing algorithms are effectively useless. Why? Hashing is actually a process that has uses that extend far beyond passwords. One of the most common uses of a hash is called a checksum. A checksum is where you download a file and you run that entire file through a hashing function and it returns a number. Then you compare that to the checksum that was provided by the person who gave you the download to make sure that no bytes were corrupted during the transfer. As a result, the most popular hash functions are incredibly fast. They're designed very specifically to calculate as many hashes as they can really quickly. Why is this problematic? Because the faster the hash algorithm, the faster a person can reverse engineer a hash. Effectively, what I can do is if I got this hash for A, actually, let's not do the hash for A, let's do the hash for 1A.
Okay.
All I need to do to decrypt this hash is to run the, just to programmatically run through all the permutations of alphanumeric characters until I find the hash function returning the same hash. Then I know that the user typed in that as their password.
Gotcha.
Now, the problem with the most popular hash functions among people who only start learning about this through the many very, very incredibly, insanely misguided tutorials online is you'll find MD5 and SHA-1. These two hash functions are designed for speed, and they are effectively useless for passwords. They can run incredibly quickly on commodity-level video cards, to the point where an entire database of salted MD5 or salted SHA-1 hashes can be cracked within days.
That's really bad.
That is bad. We don't want to use MD5. We don't want to use SHA-1. There are two other hash functions that are useful. One you see a lot from Microsoft, and I can't remember the name of it because it's not as widely used in the open source community as the one I'm about to describe. It's like PDBK, I believe. And there's another one, however. There's one called Bcrypt. Bcrypt is a very future-proof, very difficult to crack hashing algorithm, I should say. What Bcrypt is it's a hashing algorithm specifically designed for cryptographic hashing, or I should say hashing for passwords.
Okay, gotcha.
Bcrypt is slow. It can't really run very quickly on GPUs, so it's immune to GPUs. And it's future-proof.
What do you mean by future-proof?
Well, every single Bcrypt hash is actually a couple segments. The first segment, so let's say a Bcrypt hash, let's say 015x27358. I don't know if this is the actual value of the Bcrypt thing.
Okay, but yeah, just to show off.
Just to show off, I want to just show the different components to a Bcrypt. Nice thing about Bcrypt is it's future-proof because of the first value in it, which is the work factor. The work factor describes how many iterations the Bcrypt algorithm has to perform in order to successfully hash a password. The nice thing about the work factor is that a higher work factor slows the algorithm down, whereas a lower work factor speeds the algorithm up. It's future-proof because it allows for variable work factors. So today in 2013, on my local machine, I'm using Bcrypt at a work factor of 13, which takes about 500 milliseconds to compute a hash on my commodity hardware. However, in 2035, we might have super fast GPUs or super fast CPUs, and we might have to increase that work factor even more to make the hash take longer to compute. Remember, the longer to compute a hash, the faster a person can reverse engineer one.
No, the shorter to hash, the faster the to reverse engineer.
Yes.
Yeah, okay.
The faster the hash, the faster to reverse engineer. The slower the hash, the slower to reverse engineer.
Gotcha. So yeah, in the future when things are much faster, if that's got a work factor of 300, then effectively it's negated how much faster systems are at breaking that.
Right. I mean, the work factor, it only goes up to 37, I believe 37, but it gets, every new work factor is actually exponentially slower than the last one.
Ah, okay.
I bumped up the work factor to the max on my local machine just to see what it would do, and I just got bored of sitting there staring at the screen.
All right.
The next bit of security in Bcrypt is that it has an integrated salt. And again, this isn't an actual Bcrypt hash. Bcrypt hash has more characters than this. This is just for demonstration purposes. The salt of a Bcrypt hash is integrated right into the hash. See, with SHA-1 and AMD5, they don't have salts built into them. So to salt your passwords, you have to store salts in a separate database column. With Bcrypt, we don't. They're integrated into the hash itself. The final bit of the hash is the actual hash.
And salts are random, correct?
Yes, they're random and specific to a user. Or no, they're not necessarily specific to a user, they're specific to that specific password.
All right, and so that's what makes it so tough is because that random salt's already built in there. You don't have to keep it on another database so nobody can get access to those and then just crack the hash.
Right. Well, even with access to a salt, it might, or wait a second, I mean, even with access to the salt, it's not a problem. The salt just makes it, again, the salt introduces complexity for simple passwords. Because if I typed in test as a password, we don't want that to be cracked.
Yeah. Okay, I gotcha. All right.
Yeah. So we will use Bcrypt because it's slow, immune to GPUs, it's future-proof, and it has a salt built in. So that's what makes this algorithm very nice.
All right, so note is everybody should really be using Bcrypt for passwords always forever, and it's kind of like that other rule, just don't break it.
There are other algorithms out there that work as well as Bcrypt. I believe it's PDBK or PDB2 or PDPK57821. I don't know. It's another hash.
If it's hard enough to remember the name, it probably works well.
It is fairly difficult to remember the name. I should have actually pulled it up for the video, but it's a hashing algorithm that's used by it's used by some built-in Microsoft stuff. It works very similarly to Bcrypt. The only difference is that I find Bcrypt to be used more often, and I find that Bcrypt, according to the research I have done, performs worse on GPUs than the other algorithm does. And that's very important.
In this case, worse is better.
Yes. Remember, MD5 is not necessarily useless just because I put an X through it, but it's useless for passwords. Okay, so how are you feeling about this, Steve?
I probably understood this better than anything else. I don't know what that says, but yeah, I get it. So we want to use a Bcrypt to encrypt our hash. Well, I shouldn't say encrypt our passwords, but
Nope, you want to say
to hash our
Yep.
passwords.
Because the important difference is encryption is bidirectional. Hashing is unidirectional.
Okay. I'm still not sure it's answered my question why you can't reverse engineer it.
You can. You can reverse engineer Bcrypt passwords. It'll just take really, 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 really long time.
So it's really a thing of you make yourself not the easiest target and therefore not worth doing.
That is the essence of security.
There you go.
Security isn't preventing people necessarily from breaking your stuff or breaking in or doing something wrong. Security is making it so incredibly, insanely inconvenient that it is, well, practically, not theoretically, but practically impossible to break your system.
Gotcha. All right. I understand.
Awesome. So let's go ahead and actually implement Bcrypt into our system. Fortunately for us, there's only one method we need to update inside of our user entity to actually have our passwords being appropriately hashed. But first, we need to actually pull in a .NET library that will perform hashing for us. And that's going to be bcrypt.net, which I'm going to access from references, manage NuGet.
And a NuGet.
Yep. And I'm going to type in bcrypt. And I'm going to grab bcrypt.net. And I'm going to accept the license I didn't read. Okay, so now that we've done that, we can go ahead and implement it inside of our user. What I'm going to do is the set password is simply going to say bcrypt.net.bcrypt.hashpassword password with a work factor of 13. Next up, I'm going to write a public virtual bool check password. The check password function will check to see if the plain text password entered on the login form is the same password that was typed into the register form. It's actually very easy to do. We simply do return bcrypt.net.bcrypt.verify password hash. Sound good?
Wow, that's pretty darn simple for getting your security right.
Mm-hmm. Okay, I'm going to hit F6. Now, we haven't fixed our login form yet to use Bcrypt, but what I am going to do is I'm going to reset both Steve and my password so that it's hashed properly. And let me go ahead and log in because I timed out. Okay, so I'm going to reset Steve's password to test. And I'm actually going to reset my password to test too so we can see the salt in action, because it's actually going to produce two separate salts. And as a result, it's going to produce two wildly different passwords. Password hashes, I should say. So what I'm going to do is I'm going to open up users, and I'm going to select all the rows, and look what we get.
Okay, now I understand why insanely hard to crack. I get it.
Mm-hmm. So that's it as far as the create user and the reset password. Now we both have appropriate password hashes. Do you know what that means?
It means we're ready to implement that?
Well, we're ready to, implement our login form.
Excellent.
So I'm going to go ahead and log out, and I'm going to log in, and I'm going to implement this form. We still have that bell up there.
It's cute. Leave it.
I suppose. Okay, in my auth controller, on login, we're going to change this up a little bit. Instead of just blindly letting them through, I'm going to write some database code. I'm going to say var user equals database session query. Now remember, that's going to bring in nHibernate.link.
Okay.
On user, remember, this is going to bring simpleblog.models.
Okay.
Then I'm going to say first or default user, or how about you, goes into u.username equals form.username. Then I'm going to say if user equals null or not user check password form.password, then I'm simply going to write model state add model error username or password is incorrect. Then I'm going to move this if not model state is valid check to underneath this check.
Alrighty.
Finally, instead of saying set auth cookie form.username, I'm going to set auth cookie user.username. We now have passwords.
Excellent.
I'm going to hit F6. I'm going to come in here. I'm going to type in a user that doesn't exist. And in a second, once the application spools back up, we're going to get username or password is incorrect. If I type in Nelson, hit enter, username and password is incorrect. But Nelson with the password of test, hit enter, and we get logged in.
Perfect.
There's one more thing I want to address with users, and just one more thing. It's kind of important, or it's not really important. It's me being paranoid. There's a very clever way to, when using a very slow hash function as we should, to actually do a timing attack on our web server to see if a username is actually in the database. Because our hashing function takes 500 milliseconds, I can detect if the username is valid. Watch this. If I just type in garbage, look how long it took. It took 7 milliseconds, right?
Gotcha.
If I type in Nelson with an invalid password, it took 896 milliseconds.
69, but gotcha.
869, yeah. This is an example of a timing attack, and it can be used to determine if a user is registered on a website. This is getting really paranoid, but I want to point out that I think it is good practice to prevent the ability for an attacker to determine if a particular username or email exists on a service. There are a lot of services out there that would prefer it if they left their who is registered on this site anonymous. We can just leave it at
that. And it's only paranoid if they're. It's not paranoia if they really are out to get you. And in cyberspace, somebody is always.
Right. And so if they find out that your email address is registered on a particular site, or maybe your boss finds out that your email address is registered on a particular site, that wouldn't be very good. This is like kind of over the top, but I kind of like thinking of, I kind of like security. Security is fun.
Well, it's err on the part of caution.
Right. So let's go ahead and fix that. How do we prevent a timing attack when our code has different timings based off of a certain behavior? So this also applies to other security vulnerabilities with timing attacks. Well, it's actually very simple in this case. All we have to do is, if the user is null, we just have to throw in a garbage hash. Like, we just have to hash something with the same work factor, and then we'll get these exact same timings whether the user was found or not.
Gotcha.
So what I'm going to do is I'm going to open up the user model again, and I'm going to add a public static void fake hash that invokes bcrypt.net bcrypt hash password blank with a work factor of 13. I'm putting this in the user model because the work factor, I think, kind of deserves to be in here. So I only want the work factor to be known to the user class. So if we up this work factor, we should up this work factor. In fact, I can just go ahead and do a private const int work factor equals 13, and then I can just use a constant for both of those.
All right, good.
So now that I have a fake hash method, I need to invoke it if the user is null. So I want to say, if user is null, user dot what am I doing wrong? Oh, derp. There's a user property on the base controller of type iPrinciple, so we're having a little bit of a conflict. To prevent this conflict, I can simply say simpleblog.models.user.fakehash.
There we go.
Okay, so now if I rebuild, it is now no longer impossible, or it is now no longer possible, really? It's now no longer possible to know if a username exists in our database. See if I do, whoops, I just accidentally logged in properly. If I do ASDF, I get a timing of 901 milliseconds. If I do Nelson ASDF, I get a timing of about 900 milliseconds. The difference is no longer 500 milliseconds or bigger.
Perfect. Yeah, it's within the range of they can't tell.
Yep. Okay.
Nice. And this was really so little work compared to everything else we do to have security right that, I mean, you just can't emphasize it enough. Do it right.
Yep. And this way we will be pretty much, you can never say never in the programming world, but I can say that doing a bcrypt at work factor 13 will make it so insanely unlikely that you are going to have your password hashes be cracked that, and like you said, Steve, it's just so simple.
Yeah, I mean, of everything we've done, this was insanely quick, and somebody out there is going to do it the lame way, and they become the easy target, and you're safe.
We're looking at you, Gizmodo, and LinkedIn, and I have a huge list in my mind of all the people who have failed miserably at this, and I just wanted to call them all out, but I forgot the list. except for
Guys, just for the record, I didn't know that conversation was going to happen. I am not calling you out.
oh, they got called out publicly enough, so I guess I can leave them alone. They're good now.
All right.
They were embarrassed sufficiently.
In the long run, I guess that's good.
Okay, I want to do one more thing. I want to have the currently active user be available as a object retrieved from our database for the purposes of when we start adding roles into our stuff. So I'm going to create an auth class at the root of my project. It's going to have a private const string user key, which is going to be simple blog.auth.user key, and it's simply going to have a public static user with a getter. And the getter is if not HTTP context current user identity is authenticated, return null. Otherwise, var user equals HTTP context current user, or sorry, current items, user key as user. You'll notice this code is very similar to our session handling, and it is. We're basically caching an object inside of our items dictionary. Then, if the user is null, then we'll say user dot equals database session query user first or default u goes into u.username equals HTTP context current user identity name. We'll have to import system.link. Then, if user is null still, we'll just return null. Otherwise, we'll cache it into HTTP context current items user key equals user, and then return user. I just want to get this static class out of the way, which I'll mark as static, by the way. It doesn't really make a difference, but I like to be explicit. Because we will be using this down the road. All this class does is have a public static user property that we can use to retrieve a fully hydrated nHibernate entity that represents the currently logged in user. We use the HTTP context current user identity is authenticated to see if they're logged in, and then we retrieve their username out of HTTP context current user identity name. We use that to grab them out of the database. We then cache their object into our HTTP context current items, and we return it.
All right.
And I think that pretty much wraps up our lesson on hooking up authentication to our database.
Excellent. Let's move on.